In Episode 10, titled IPv6 Strategy in Hybrid, Adoption Patterns, Common Pitfalls, and Exam Queues, we frame Internet Protocol version 6 as coexistence planning across mixed environments, because most real organizations do not flip a switch from one protocol to another overnight. Hybrid environments include on-premises segments, cloud networks, remote users, and third-party connections, and those pieces rarely move in lockstep. The exam tends to test whether you can reason through coexistence choices and spot where assumptions break, not whether you can recite every address format rule from memory. When you treat Internet Protocol version 6 as a planning problem, you focus on reachability, name resolution, security controls, and operational visibility across boundaries. That approach also helps you interpret exam queues because many scenario prompts are quietly describing coexistence friction rather than pure Internet Protocol version 6 deployment. The goal is to make your decisions feel grounded and predictable even when the environment is mixed. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Addressing basics are the first anchor, and the most useful way to remember them is by intended scope rather than by memorizing long hexadecimal examples. Global unicast addresses are intended to be routable across the broader Internet and across routed networks, and they are the Internet Protocol version 6 equivalent of public reachability when policies allow. Link local addresses exist on a local link and are used for neighbor discovery and local communication, and they are present even when you do not explicitly configure global addressing. Unique local addresses are intended for internal use, similar in spirit to private addressing in Internet Protocol version 4, and they are typically used within an organization where global routing is not desired. The key point is that scope drives behavior, because routing, filtering, and name resolution depend on whether an address should be reachable beyond a local segment. In exam questions, when you see language about local segment behavior or automatic configuration, link local scope is often part of the story, even if it is not named. Dual stack is a common coexistence pattern, and it makes sense when you need both Internet Protocol version 4 and Internet Protocol version 6 reachability simultaneously, because different parts of the environment and the client base support different protocols. Dual stack can be a practical bridge when you cannot control all endpoints, when you must support external clients, or when third parties still rely heavily on Internet Protocol version 4. The risk is that dual stack adds complexity because you now have two paths, two sets of policies, and two opportunities for misconfiguration, and those risks show up in troubleshooting and security posture. Dual stack also introduces subtle behavior choices because clients and applications may prefer one protocol over the other based on resolver results and connectivity. In some environments, dual stack is the safest short-term move, but in others, it can double the attack surface and halve the clarity if controls are not mature. Exam scenarios often reward recognizing when the added complexity is justified versus when it is an avoidable risk. Transition mechanisms like network address translation 6.4 are often introduced when parts of the environment are Internet Protocol version 6 only, while other resources remain Internet Protocol version 4 only, and that is where common dependency assumptions can break. Network Address Translation 6.4 allows Internet Protocol version 6 clients to reach Internet Protocol version 4 services through translation, but translation changes the visibility and sometimes the behavior of connections. Many systems assume end-to-end addressing consistency, and translation can break assumptions about logging, client identity, and policy enforcement because the observed source may not reflect the original client cleanly. Dependencies can also break when applications embed literal Internet Protocol version 4 addresses, when allow rules are written only for one protocol, or when monitoring tools do not capture translated context accurately. In hybrid environments, translation can be a practical stepping stone, but it should be treated as an operational and security complexity multiplier rather than a magic bridge. On the exam, options that propose translation often come with trade-offs around troubleshooting, logging correlation, and policy consistency, and those trade-offs should be part of your selection. Router advertisements are a quiet but powerful part of Internet Protocol version 6 behavior, and they influence client configuration in ways that can surprise teams accustomed to purely manual Internet Protocol version 4 assignment. Router advertisements can inform clients about the presence of a default gateway, available prefixes, and configuration parameters, and clients can self-configure addresses based on these advertisements depending on the environment settings. The silent nature of this process is the key exam-relevant point, because changes to router advertisement behavior can shift client routing and address selection without anyone touching the client directly. In a mixed environment, a single misconfigured router advertisement can cause clients to prefer an unintended path or select an address type that does not work beyond the local segment. This can look like random reachability failure, especially when some devices behave differently based on operating system defaults and configuration. When a scenario describes sudden behavior changes after a network change with no client updates, router advertisements should be in your mental model. Domain name system considerations often decide whether coexistence feels smooth or chaotic, because name resolution influences which protocol clients attempt first and how failover occurs. Internet Protocol version 6 uses Quad A records for address resolution, and the presence of Quad A records alongside traditional records can change client behavior. Resolver behavior and priority rules determine whether a client attempts Internet Protocol version 6 first, whether it falls back quickly, and how it chooses between multiple returned addresses. In some cases, a client may prefer Internet Protocol version 6 even when the Internet Protocol version 6 path is partially broken, creating timeouts that feel like application slowness rather than a clear connectivity failure. In hybrid environments, inconsistent domain name system entries can create split behavior, where some users resolve to one protocol and others to another, complicating both troubleshooting and policy enforcement. Exam cues often include mention of name resolution, inconsistent reachability, or differences across clients, which should push you to evaluate domain name system consistency and address record strategy. Security implications of Internet Protocol version 6 are often misunderstood, and the exam tends to test whether you recognize practical differences without falling for myths. The larger address space does not automatically make an environment secure, but it does change scanning economics and can influence how discovery and enumeration occur. Filtering strategy must explicitly include Internet Protocol version 6, because policies written only for Internet Protocol version 4 leave a parallel unfiltered path that attackers can use. Visibility gaps are common during transitions because monitoring tools, log pipelines, and security analytics are sometimes configured with an Internet Protocol version 4 mindset and may not normalize or highlight Internet Protocol version 6 activity properly. Neighbor discovery and router advertisement behaviors also introduce local link dynamics that need to be monitored and controlled, particularly in internal networks. In scenario questions, a correct answer often emphasizes consistent policy enforcement and logging across both protocols rather than treating Internet Protocol version 6 as a side feature. The security story is not bigger is safer. It is different requires deliberate control. A frequent pitfall is incomplete firewall rules and forgotten Internet Protocol version 6 enablement paths, because coexistence can create a hidden backdoor when teams focus only on the familiar protocol. An environment may have strong Internet Protocol version 4 filtering, while leaving Internet Protocol version 6 allowed by default, which effectively bypasses intended segmentation and ingress controls. Forgotten enablement paths appear when operating systems enable Internet Protocol version 6 automatically, when cloud networks support it by default, or when devices begin using it for local communication without explicit configuration. This can create unexpected reachability that no one planned for, and it can also create unexpected failures when applications choose Internet Protocol version 6 paths that are not fully supported. The pitfall is not the protocol itself. It is the assumption that disabling or controlling Internet Protocol version 4 is sufficient. Exam scenarios often hint at, "We never configured Internet Protocol version 6, or "We only wrote rules for Internet Protocol version 4. And those hints should immediately raise suspicion about parallel path exposure. Consider a scenario where an organization is expanding into a new cloud region while maintaining on-premises services, and remote users report intermittent access issues after the change, especially when connecting from newer devices. An Internet Protocol version 4 only approach could be simplest if all dependencies, external partners, and monitoring are built around it, and if there is no strong driver for Internet Protocol version 6 in the near term. A dual-stack approach could be appropriate if the cloud region and many clients support Internet Protocol version 6, but the organization still must support Internet Protocol version 4 services and external connectivity, and if controls and monitoring can be applied consistently to both. An Internet Protocol version 6 only approach might be attractive for a new isolated segment where the organization controls all endpoints and dependencies, but it is risky in a mixed environment if translation or compatibility gaps will dominate operations. The best answer in such scenarios usually balances reachability and risk, favoring the option that can be governed and observed rather than the one that is ideologically modern. The exam is testing judgment about coexistence maturity, not enthusiasm. Troubleshooting queues when Internet Protocol version 6 breaks reachability unexpectedly during transitions often come down to recognizing that the client may be choosing a different path than you assume. If some clients fail while others succeed, especially across different operating systems or device generations, suspect differences in Internet Protocol version 6 preference and fallback behavior driven by domain name system and local configuration. If failures began after a network change and no clients were updated, suspect router advertisement changes or gateway behavior that shifted default routes. If reachability to some services fails while others work, suspect incomplete policy enforcement, where Internet Protocol version 6 is allowed or blocked differently than Internet Protocol version 4, creating inconsistent access. If the symptom looks like slow application response rather than a clear failure, suspect that clients are attempting Internet Protocol version 6 first and timing out before falling back. In exam logic, the best troubleshooting-oriented answers point you to confirm which protocol is being used, whether name resolution is returning expected records, and whether policy and routing are consistent across protocols, without jumping straight to application changes. A memory anchor for address types is to tie each to its intended scope, because scope is what determines routing expectations and typical usage patterns. Global unicast belongs to broad routing, where the intent is reachability across networks, which makes it the default for internet-scale connectivity when policy permits. Link local belongs to the local segment and is tightly tied to neighbor discovery and local operations, which makes it always present and often the silent actor in automatic configuration stories. Unique local belongs to internal organizational use, where you want stable internal addressing without advertising it broadly as a globally routable identity. When you remember scope first, you can infer behavior, because you know whether an address should be reachable beyond a link, beyond a site, or beyond the organization. This anchor helps in exam questions where the correct answer depends on whether an address type is appropriate for a given connectivity goal. As a recap prompt, compare coexistence options and their trade-offs by focusing on operational simplicity, security consistency, and dependency compatibility rather than on protocol preference. Internet Protocol version 4 only offers simplicity when the environment and dependencies are aligned, but it can limit future readiness and may not match external requirements in some contexts. Dual Stack offers broad compatibility and a gradual transition path, but it increases complexity because you must secure, monitor, and troubleshoot two protocols with equal discipline. Internet Protocol version 6 only can simplify future operation in a controlled greenfield segment, but in mixed environments, it often shifts complexity into translation mechanisms and hidden compatibility issues. The best choice in the exam context is usually the one that aligns with the organization's ability to enforce controls and maintain visibility across the chosen approach. When you can compare these options quickly, you are less likely to be tricked by an answer that sounds modern but ignores the operational reality described in the scenario. To close the core with a rehearsal, describe client behavior under router advertisements, because this is where many mysterious transition failures originate. A client on a link receives router advertisements that can indicate a prefix and a default gateway, and the client may self-configure an address and route selection based on that information. If router advertisements suggest a viable Internet Protocol version 6 path, the client may prefer it when connecting to services that have corresponding domain name system records, even if the path is partially broken beyond the first hop. If the Internet Protocol version 6 path fails slowly, the client may appear to have application slowness while it waits to fall back, and different clients may fall back at different speeds. This behavior is silent from the user perspective, which is why it becomes a troubleshooting challenge and an exam cue. When you can narrate this flow, you can reason about why a change in one network segment can affect many endpoints without any endpoint configuration changes. In the conclusion of Episode 10, titled IPv6 Strategy in Hybrid, Adoption Patterns, Common Pitfalls, and Exam Cues, the key is viewing adoption as coexistence planning across mixed environments rather than as a single migration event. You understand the scope-driven roles of global unicast, link local, and unique local addressing, and you recognize when dual stack is justified versus when it adds unacceptable complexity. You account for transition mechanisms such as network address translation 6.4 and the dependency assumptions they can break, and you treat router advertisements and domain name system behavior as major drivers of client protocol selection. You address security by enforcing consistent filtering and visibility across protocols, avoiding pitfalls like incomplete firewall rules and unintended enablement paths. Recap the adoption plan by choosing the coexistence model that matches operational maturity. Then assign yourself one coexistence comparison exercise by taking a single scenario and defending an Internet Protocol version 4 only, dual stack, and Internet Protocol version 6 approach in turn, focusing on trade-offs rather than ideology. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.